The formula a equals pi r squared shows that area is a quadratic function of the radius of a circle. The formula r equals 1 over the square root of pi times the square root of a shows that the radius of a circle is a square root function of the area. A square root function is the inverse of a quadratic function that has a restricted domain. A horizontal line can intersect the graph of f of x equals x squared in 2 points, where f of negative 2 equals f of 2, as shown below in the graph. Note the parabola, representing f of x equals x squared, and the horizontal dashed blue line at y equals 4, intersecting in 2 places, both at f of negative 2 and at f of 2. Thus, a vertical line can intersect the graph of f inverse in 2 points. Note the graph on the right. F inverse, a parabola that opens to the right, and now a vertical line at x equals 4, intersecting the graph in 2 points. F inverse is not a function because it fails the vertical line test. However, you can restrict the domain of f so that the inverse of the restricted function is a function. Note on the left, if we restrict the domain of the original function f of x so that x is all values greater than or equal to 0, f inverse of that function with the restricted domain is a function. Inverses of the power functions, y equals x to the n power, with domains restricted as needed, form parent functions, y equals the nth root of x, for families of radical functions. In particular, f of x equals the square root of x is the parent for the family of square root functions. Members of this family have the general form f of x equals a times the square root of x minus h plus k. Alright, take note of the information on this slide, but we'll see this information in greater detail in the future slides. Families of rational functions. First, the parent function of the square root functions y equals the square root of x. Here we see it graphed. Reflection of that graph in the x-axis, well, that's y equals the negative of the square root of x, graphed here and reflected about the x-axis. Introducing the coefficient a of the function the square root of x. If a is greater than 1, we stretch the graph vertically. If 0 is less than a is less than 1, we shrink the graph by the factor a. Note the graph on the right. If a is 2, the graph is stretched vertically by a factor of 2. If a is 1/2, the graph is compressed or shrunken by a factor of 2. Now adding variables h and k as shown in the equation. These cause translations, a horizontal translation by h and a vertical translation by k. Note the parent function, graphed in black, y equals the square root of x. And then in orange, y equals the square root of x plus 1 in the radicand alongside the x, the input values, causing a horizontal translation to the left 1 unit, and minus 2 outside the square root, causing a vertical translation down 2 units. Note that similar transformations occur in the family of radical functions. Problem 1. Translating a square root function vertically. What are the graphs of y equals the square root of x minus 2 and y equals the square root of x plus 1? The graph of y equals the square root of x minus 2 is the graph of the parent function, y equals the square root of x, shifted down 2 units. Take note of the graph, the parent function graphed in black, and our translated function in blue, each point shifted down exactly 2 units from the parent function. The graph of the square root of x plus 1 is the graph of the parent function shifted up 1 unit, as shown in orange. The domains of both functions are the set of non-negative numbers, but their ranges differ. For the blue function, the range are all y values greater than or equal to negative 2, and for the orange function, the range are all y values greater than or equal to 1. Your turn. What are the graphs of y equals the square root of x plus 2 and y equals the square root of x minus 3?